I got my start at Los Alamos National Laboratory, which is a U.S. Department of Energy lab in the United States. And our mission was and is to protect the country through advanced science. And so as a consequence of that, we needed to be 10, 15 years ahead of industry. And so I got started in about 2000, which turns out is quite a while ago now. Fairly quickly into enterprise network security and mostly detection of attackers inside of an enterprise. And it's funny because one of our first projects, I think the title was something like, "Are data-driven methods appropriate for cybersecurity?" So in the early days, it was signature matches and very heuristic sorts of things, and it wasn't really data-driven. And I think in the intervening years there, we did say, yes, data-driven methods are appropriate. Something perhaps self-evident today, but had many successes, and I think actually were 10 or 15 years ahead of industry at that time. And in fact, some of the things you'll see today are the translation of the work we did in the government into industry and at scale. And so a lot of this is influenced by those early days. Well, I'm a one-trick pony. I've been saying the same things for 15 years, where we had some good ideas, they worked well, and now I'm in industry to put them at scale. And so a lot of this is about how do we do this for millions of machines and thousands of organizations instead of one organization and 100,000 computers. So with that, what's the setup? So I'm mostly focused in post-breach. So we're talking about an enterprise. We're not talking about consumer cybersecurity here. We're talking about an enterprise network. And the attacker has already penetrated the perimeter defenses. So they've phished. They've somehow obtained a credential that's valid for the network, and they're able to log in past the sort of antivirus and firewall defenses in the enterprise. And once you get there, well, you've eliminated most of the easy things, and the millions of attempts to penetrate a firewall per day. These are the very few that have been successful. And so they're smarter, and they can be extremely well-funded nation-state organizations which are professional and scientifically rigorous in their attacks on our networks. These are good bad guys, effective, professional folks. And so it's pretty hard to find them. And they don't tell us what they're doing. They don't call us and say, we got in over here, and then we moved to this computer, and then we stole this data. So we don't have labels, right? So supervised machine learning is not really on the table here. I should back up and say that to give you a broader perspective, so antivirus has had a renaissance in the last few years in which antivirus software started out as signature matches. We have an example of malware, and then we take a hash of that, and then we match it against the files we're seeing in the enterprise, and if it matches, we set off an alarm, right? That doesn't work very well. The adversary can recompile with some different options in the compiler, and they're around those signatures. So the next thing that happened, and this is again something that the government was doing early but is now being done at Microsoft and other places, is they take the executable and they put it in a detonation environment. And this means they put it in a virtual machine and they execute it, and they extract behavioral features from the execution itself, and then Supervised machine learning comes into play on these feature vectors, and they do a lot better because this is a much more general thing. You can't recompile and get around the behavioral features that are being extracted, right? So it's much harder. And so in terms of antivirus, we sort of look at that as a pre-breach sort of behavior. It's before they get in. Once they have executed that malware on a given machine, we're now in post-breach settings. So I'm giving credit to supervised machine learning in terms of its ability to detect malware. And that's mainly because we have giant labeled data sets of malicious software and benign software. And it's a very restricted set of behaviors. It's pretty hard to exploit an operating system at this point. So we don't expect a lot of variability in the behaviors that are able to exploit a piece of software. And so the supervised setting works in that we have lots of labels. And we expect that those labels, or the feature vectors that are extracted, are representative of future attack behaviors because they're very constrained in what they can do anyway. Post-breach, different scenario. We don't have a lot of labels. They don't tell us what they're going to do or what they've done. And they have lots of flexibility. And so this picture is meant to sort of show you that, well, to start out, the little dots are computers. The lines between the dots are communications, or in this case, authentication events between computers. So this is a visualization of an enterprise. And the little tiny red dots that you might not even be able to see, that's a real attack. So I'm visualizing this is a real attack on the network. And what I'm trying to do here is say, it's hard to find them. They're a needle in the haystack. And they have a lot of options. You can imagine that there's a combinatorial number of things they could do. And so, even if they told us what they did and we had labels, we don't expect that those labels would be representative of the different options that an attacker would have in the future. So that even a labeled data set would not be very representative of future attacks. Okay, so then our only hope is anomaly detection. And that's what most of this talk will be about, is unsupervised settings where we're deploying statistical methods to understand normal behavior and detect deviations from that normal behavior. That's the approach. Okay. I have to have a needle in a haystack. I think when you talk about anomaly detection, you have to. It's required. I'm in the Society of Anomaly Detectors, and they require that one of my slides has a needle in a haystack. But I think I'm going to take it out. I'm sort of, it's old hat at this point. But the goal here, and this is all going to be quite high level, so I really won't dig in much on the details, but model everything about an enterprise. And so establish a good understanding of a given user's login behavior to a given machine. That's a model. Establish a different model for when they log into a different machine, or when it's a different user logging in. So you can understand that there are millions and millions of models that we deploy on a given enterprise to understand at high resolution behaviors in the enterprise. And I'll talk a little bit about models. In Cole, we'll talk quite a bit more about models that we use. But it's basically, we would like to have at high resolution an understanding of what's normal in the enterprise. And a lot of questions come up like covariance. And so how complex are these models? For purposes of scale, we typically do univariate models, simple models, and assume independence when in fact they are not independent. But there are many reasons, and I'll talk a little bit more about why we assume these things, what kind of scale we're talking about. But in the end, they're quite simple, and they make assumptions that are not correct so that we can scale. Once you have a good understanding of normal behavior, and you can quantify deviation from normal behavior in the data that you're observing right now, that's not enough for good detection. because it turns out rare events happen all the time in a computer network. And if you can imagine, if you put 500,000 humans under nearly continuous monitoring, that one of them is going to do something weird every minute of every day. And guy gets in a fight with his wife, and he comes in the middle of the night, and we don't have any data for that, and yet it happens. It's a rare event, and we don't have the telemetry for it, so our model isn't quite right, and so it'll say this is rare, and yet it's not an attack. Did you have a question? Or?
No.
Oh, okay.
No, this is
sorry.
Fine.
Okay, and please do interrupt. This is casual. We have time here, so please do ask questions. Yeah, there's a microphone here for questions. So yeah, rare events happen, and they're not necessarily an attack. The guy that got in a fight with his wife is not a threat to our network. It's just a rare event. And so the next step after understanding what's normal in the network is to then, and quantifying deviation, is to then combine rarity in ways that's consistent with attack behavior. And so you can go from weak signals to strong detections by combining these things in ways that are consistent with attack behavior. And that's where a lot of domain knowledge comes in, and that's where we're lucky enough to have it turns out we made the operating system for many of these attacks. So we can talk to the people that developed the operating system, for one thing. We can also talk to all our threat experts who understand attack behavior. Many of them are white hats or sort of gray hats. They know what attacks look like. They build attacks. They reverse engineer attacks. They've been operational in terms of protecting networks for a long time. So we're buddies. We hang out. We go have beer together. We spend a lot of time in close collaboration with domain experts. And that's where we get the cyber knowledge introduced along with the statistical modeling to form questions such that when the answer is that's rare, it's also an attack. And this is not trivial. This is hard work. So a vision, so to speak. I mentioned it. Establish models that can quantify normal behavior in detail, and then quantify deviation, and then combine it together in ways that are consistent with an attack. So I'm going to talk about an attack. This is a cartoon. It's kind of funny that a Microsoft guy isn't very good at PowerPoint, but here you go. So let's see, I'll be pointing on this screen, or maybe I'll be pointing, I apologize to this, but the majority of the audience is over here. So on the left is, well, each circle is a computer. The lines between are communications or authentication events or emails or some other sort of thing we can measure between computers. The dashed line is the perimeter of the network. So to the left of that leftmost, to the left of the leftmost node is outside of the enterprise. It's on the internet somewhere. And so what are we looking at? This leftmost machine is an attacker on the internet sending a phishing email. The set of edges here, communications, are the sending of a phishing email to the enterprise. Because we have established models for normal emails coming in, we can quantify each of those emails being sent in terms of its deviation from what we're expecting. And that's fairly vague. I'll tell you a little bit more about that. So some obvious things that come to mind. If they make a grammatical mistake, if they make a spelling mistake, that's going to contribute a tiny little bit of signal. Not very much, because normal users also make grammatical mistakes, and very good attackers don't. So it's only a small bit of signal. Another thing about this. The set of users or machines that received that email, accounts that received that email, may be unusual with respect to how this enterprise receives emails in groups. For example, I don't receive a lot of emails that our CEO, Satya Nadella, also receives. So if we both receive one, that has a bit of rarity to it. Not very much. There's not a lot of signal in this, but there's a little bit. And that's the sort of point is, there's a little bit of signal there. From that initial thing, well, it turns out some users click. And this has been a hard lesson for cybersecurity to learn. Users will click on emails. No matter what you send them, they'll click on it. Some portion of your population will click on an email. When they do, actually this is perhaps not quite accurate, but you can see alpha 8 there is a reaching back to the sender of the email to get some malware. And actually, typically, but that is actually another node on the internet, some command and control server, a web server that's been compromised that's going to serve them malicious software. Once that happens, they'll exploit something in the operating system, or they'll just ask for a password, and users will happily enter their password into random websites on the internet. Please don't do this. Please don't do that. Don't click on things, actually, ever. But obviously you can't do that. So in one way or another, the attacker is going to have valid access to this node here, with a score of alpha 4. And you're starting to get the idea that the alphas. Sorry, I didn't quite mention this, but the alphas are deviations from expected behavior, and so in statistics we call these p-values. But they're higher, so they are the probability of the data we're observing under the model. And so low values of alpha are concerning, or rare, at least rare, with respect to our knowledge. So we're going to assign a score to that. Communication back to the command and control server. Once they're on the network, they're in that node. They're going to conduct a bit of reconnaissance. So they're pretty highly motivated to not stay in that initial place for a couple of reasons. One is we have pretty good defenses for that initial penetration. So we have machine learning models that can take up to 24 hours to decide whether we've been compromised in terms of the antivirus. I was talking about that earlier, the sort of supervised machine learning, including deep learning models that take into account population behaviors and quite large. And so they take up to like 24 hours. So the attacker, when they get in, they know the clock is ticking and they need to move off of that machine because we're going to probably shut that machine down fairly quickly. So they're motivated to get off of it. The other reason is that it's probably some user's laptop. It's not this laptop because that's mine and I don't click on those things. I might. But valuable enterprise data is probably not stored on this computer. Some, but not a lot. And what they're looking for are the real crown jewels of the organization. You know, they're looking for our intellectual property. They're looking to get to our domain controllers, which have credentials for the whole enterprise. If you compromise a domain controller, you can steal everybody's password for the entire enterprise. And so then you can log in as anybody and do anything you'd like. And so they're motivated to move off of this initial foothold. And yet they don't really know much about the network, which is something we really count on. This is why deviation is important, is because we can know our network, but they don't actually know the normal operation of our network. It's our only advantage as defensive people. And so they had to do some exploration. So this next set of behaviors, alpha 15, 16, 17, and 18, are reconnaissance inside the network. And this typically is in the form of port scans. So they're emitting deviations in network behavior, which are sort of like, are you listening? Are you listening on a web port? Can I log into you? Do you like my credential? They're trying to see where else they can get and what kind of data is out there. And so that's where these alphas come in. A lot of those come in from port deviations in network communications. They'll find a place that they like, in this case, alpha 12. I'm sort of overloading the term alpha. Alpha is a deviation score, but the node corresponding to alpha 12. To do that, they just RDP, so they remotely connect, or SSH for you Linux nerds out there, of which I'm one, actually, a stranger in a strange land. And so they'll log in, they'll have some kind of interactive login. Alpha 12, and then they may continue that process. So this is called lateral movement. They'll log into a machine, they'll see what kind of data is on it. They'll try to escalate privileges. So once they have access to a machine, there are methods to dump memory for other credentials. So other credentials that are existent on that machine can then be accessed by the attacker, and then that allows them to sort of further escalate privileges. So you can imagine, like, if a local area admin logs into this machine here, alpha 12, then their credential is stored on that machine in memory. And so when the attacker comes along, they can grab a hold of it, and now they have access to all that local administrator's access. And so they're escalating privileges. They're moving from machine to machine. You can imagine that actually there's an iterative process where they'll land on a machine, do more recon, lateral, do more recon, and so forth. And so that may be actually extended graph here that I'm not representing. But at some point, they've found the data that they like, and they're ready to steal it. And so this last bit here, represented in the node corresponding to the score alpha 19, are a set of staging behaviors where they're moving data from a variety of machines in the network into a central place, and then they're going to zip those or tar them or rar them or some kind of archive, get them all together, and exfil out of the network. Steal it out at that last final step. So that's the kill chain. That's what we call the kill chain. The set of behaviors that an attacker does to penetrate a network, get the right data, and steal it. The punchline is, we can quantify these deviations, and then even if they're weak, in combination, they can be very strong. And so if we see these rare events all together in this sort of subgraph, then we can score them. And so there's one which actually, if I put a 2 in front of there and took out the WI, this would have a distributional thing, and we could call it a Fisher score. And actually, there's an expert in the room, Nick Hurd, and Patrick as well, as somewhere in the back there. Here, Patrick and Nick in the back, who have written a nice paper on other methods for combining and why you would use other methods, in what situations you'd use other methods to combine. But eventually, the punchline is combine this together, and that's going to be a much stronger way to find bad guys than if you consider these things individually. Couple of advantages to this. So I said earlier we sort of assume independence here, and so you can see in this that it's the sum of logs. It's like a product, and the product of probabilities sort of has an independence assumption that these are not independent. They're not independent even under the null hypothesis of there is no attack present, right? So it's convenient. It allows us to run models individually on each of these behaviors in parallel on giant compute systems that we have. It also scales, and this is sort of subtle, it's something I only learned recently, is it scales in terms of researcher time. So I can have a researcher work on one bit of this, and then some other researcher work on some other bit of this, and then I can just combine them together, and they don't have to collaborate with each other. They can do this at universities and in Microsoft, and we can sort of bring all these together. So that's maybe only the managers in the room would be interested in that, but it's quite powerful idea, and it means that Microsoft can collaborate, and this is a bit of an advertisement. We like to collaborate. You need a microphone, I believe.
I go to the shout. Do you have any sense as to... I can also have a microphone.
Yeah, because it's being streamed, so.
Do you have any idea how much you lose by making that independence assumption?
That's a great question. Ouch. It's a tough question, and it's actually a question about what we're missing. So I'll say that we can quantify our false positive performance fairly well. So when we fire and it's not an attacker, we can know that, right? Because something to explain is we have a set of graders, and what they're 15 of them, and what they do is they look at our alerts and they say that was true and that was false. They sample. They don't look at all our alerts, but we produce a lot of them. But they give us some indication of true and false positives. What they don't tell us about is our recall or the things we're missing, because they don't know about them and we don't. You know, it's this sort of unknown sort of thing. So that's a bit more of a challenge. But I think the main impact is that an assumption of independence when independence is not present leads to more false positives. Because ultimately it leads to a worse understanding of the normal behavior. And so then we'll call things rare or we'll call things an attack that actually aren't. And I haven't given you a satisfying answer. To quantify these things is difficult because the attackers don't tell us what they're doing. And so to be really sure. So we could probably do it under simulation. We can do it under red teams, that come and attack our networks because we ask them to. And then we have ground truth, and then we can say. But I think in general, this is a challenge in the industry at large, is that the attackers are doing things that we're unaware of. They're constantly innovating. Their job is to do new stuff, because anytime they do something that we've already seen, we probably have a way to detect it. So these people's job is innovation, which is pretty cool. We like innovation too in this room, right? So we're all researchers. They're researchers, and their whole goal is to do new stuff. And therefore, man, it's hard to quantify, our assumptions.
Sorry.
It's okay. I can repeat your question.
I lost my microphone.
That's okay.
But you were mentioning that you're scaling research time because you're giving each of them a separate model.
Yes.
If you gave one researcher a non-independent model,
Yes.
where they do try and model the joint distribution,
Mhm.
and you give two other researchers their single
Mhm.
model, and then you see,
Mhm.
and then you take all your historical data and
Yeah.
you rerun it, that would give you a way of quantifying
Sure.
how much you're losing.
Yeah.
No?
Yes.
Sorry.
Yeah. So the comment for the record is we could try it out. So we could have independent models, and then we could do a joint model, and we could compare the difference. And the fact is that in cases we have, and we've written papers about that in various ways, and the guys at Imperial have done some work there as well. But I guess my general feeling is that, yeah, we can do these kind of studies, but in the end, the attack behavior is non-stationary, and the defender behavior is non-stationary, and the network we're trying to defend is non-stationary. And so these are pretty academic questions, and for operational security don't matter that much. But fodder for papers. And if you're interested in that, we are interested in collaborating on such things. So I don't mean to poo-poo your comment, and I think it would be important for an academic contribution. For operational security, it's less important. Yeah, 2 questions.
Obviously, this is a cartoon, but it seems to me that this is essentially a passive response. You are analyzing things. Is this not a mechanism to develop good honeypots? That you can actually draw them and discriminate in nearish real time, and draw them and actually confirm whether their behavior, simulate a domain control. You're nodding your head, so I'm telling you something you know already.
Yes, and probably I should be careful about comments around that subject. I'd hate to tip the attackers too much, but you're right. I think I'm more. I'll go a little further into things that are a bit futuristic. But the way I think this is headed, and we're going to digress a bit here, but it's okay because we have time, and maybe this is interesting, is I'm expecting that interactive attackers are going the way of the horse and buggy. and that in the end, these kind of attacks are going to be automated, and that they're deploying AI, if you will, as we are. And so you can imagine that, like perhaps people in this room are thinking, hey, I could write code to do that instead of having an attacker do it manually with hands on a keyboard. And so then, as defensive people, we think, well, okay, let's code that up. Let's deploy it. Let's deploy automated attacks against ourselves and see how well we do, right? And then I think the next evolution from that is then let's have the defense learn from those attacks automatically. So that you could imagine a game that's being played where the offense and the defense are learning from each other in an automated fashion in order to tune defensive capabilities. And then you worry about things like bias and the assumptions we encode in the attack models, tuning our defenses, and then the attacker has these big gaping holes where we didn't, we made assumptions. That's a concern, yes. Another one is we're launching weaponized attacks against ourselves, and that may be a bad idea. So we have to think about controlling these things in some way, have a kill switch of some kind, because they may spread exponentially and destroy our networks, and that's not the intention. But I think it's a very interesting thing, and so I'm sort of taking your question and changing it a bit so that I can be careful, but also I think it's right on, and it's a relevant thing to ask. Yeah. Over here, yeah.
So two small questions. One, like how high dimensional is the space you're considering? Like how many variables or p-values are you considering? Because it kind of relates to the earlier question about like how you do multivariate modeling on this.
Yes. Enormously high dimensional. I might have a slide on this. I might have a slide in a bit, but so I haven't told you much about the product. So I work for Microsoft Defender Advanced Threat Protection, and that's an endpoint agent. And it measures stuff from the operating systems of our enterprise customers who have signed up for the right service. And it's doing that in near real time, and it's measuring lots of stuff about the operating system and then shipping it to Azure, and that's where all our code runs, okay? So what do we measure? Well, we measure network behaviors, we measure file accesses, process execution, the process tree, which is, you have parent, child, you have a whole high dimensional tree. Did I mention registry changes, library calls, PowerShell uses, script execution, command lines and from things. So I'm trying to give you an idea that like in each of the nodes, a many-dimensional vector, and then between nodes, the network and the credential behavior. And then how many nodes are there? More than 1 million in some cases. So now, and this is over time. So every at a high resolution, we measure these things. So now it's sort of insanely large. Millions and millions of covariates. So
the next question was going to be, where do you get the weights from?
Yeah, good question. Well, I could make some things up. So by that I mean that I could use my threat experts to tell me that this bit of behavior is more concerning than that. I could use some label data, and like I said, we're grading. So we're saying that was a true positive and a false positive at sort of massively subsampled rates. But those things could be learned. And so in fact, the WI is meant to sort of insert some supervision. And how do we get it in any way we can? But I think, the Bayesians in the room are probably thinking about priors and things. And I think that's a good idea.
So kind of in a very semi-supervised setting.
Yes.
Strongly geared towards the unsupervised.
Yes, that's right. That's right. And so you can think about labels with noise, and the graders aren't perfect, and then they're very sparse labels. So yeah, it's sort of weak, semi-supervised learning. Yeah. Yep. Good questions. Nick, just throw it. Just throw it to him. No, don't throw it to him. Don't throw it to him.
Just to answer that question, there's sort of like a mathematical answer to how you would choose the weights, in the sense that if you didn't have the weights, then you're assuming mathematically that the p-values are beta A1
Yeah.
for some A.
That's right.
And so if you've got weights, you're assuming they're beta A over WI. So
A over
that's
WI.
explicitly what they mean.
Right.
for what it's worth.
Yep. Thank you. Yep. And I think maybe Cole, will you? Yeah. So Cole will talk about that some. Nick, so you've teased us a little bit. That's a good comment. Thanks. Another question? Yeah. Great. Thanks for the interaction. It's great.
So we do endpoint security. So I work for a company based in Cambridge as well, a subsidiary of ARM, and we do trusted execution environments coupled with strong user authentication. So
Yes.
coupled that with extremely sort of extremely robust access control, how does that change the baseline through which you can then identify trusted endpoints and strong authenticated user behaviors versus those that are less? Does that impact at all in terms of your modeling?
Yeah, not really. And so I mean, I can see why you're asking the question, but the scale at which we do these things, and there's so many computers under monitoring that we prefer, at least for convenience, I suppose, methods that are blind to individual things and just use the data to tell us what's rare. And I think your comment would make things better. So what I'm not saying is that that's a bad idea, but what I'm saying is that we haven't got around to it, and it's because of our giant scale that we're not sort of being specialized in terms of the baselines. Where I'd like to get to is much more sophisticated models that are. I don't trust the customer, in that. That's sort of maybe the wrong thing to say on the record, but they have limited understanding of their own networks, and so I would prefer to measure from the data what those behaviors are. But I think I can identify these strongly authenticated accounts and so forth from the data, and then have automated ways to treat those separately with different models and different baselines, and be much more specialized in terms of how I deploy my models. And I think Cole will talk some more about this, but where we're headed is automatic model selection as well as model fitting, where we can deploy a system that will learn the right model. I shouldn't steal any thunder here. Learn the right model, fit the data, and then have a monitoring process on top of it to say that model no longer fits, and try to do this fully automated, in which it would have these sort of specialized models for specialized assets in specialized organizations and so forth. Thank you. Thanks. Okay. Let's keep going. How am I doing on time? I'm in about 30 minutes in. So. This is just another cartoon of a sort of my conceptual understanding of the conceptual architecture that we deploy for anomaly detection at scale. So you've got a variety of sources, and I sort of listed a few coming in. And then you have models. So P0 through PK are different models. They're scoring the data, producing these S0s. Those scores, or p-values, go into calibrators because it turns out the models don't always fit. And I would mention this, the guy comes in at night because he got in a fight with his wife. That never happens to me, by the way, in case my wife is listening. And we didn't measure that, and so our models don't fit because of those things, because of missing stuff. And because of scale, these things and independence assumptions and things that, the models aren't accurate. But what you would hope, and Cole's going to talk about, this is actually a teaser for Cole's talk. In many ways, he's going to get into some of these modules a lot more. But the models are not fitting, and so if the models were fitting, one of the things that you would hope to get out of calibration is that the output of the model should be uniformly distributed 0, 1 under the null. Okay, that is. Every score is equally likely under the null. Otherwise, one of the models may inordinately influence the combined inference that's happening in this next step. So you can imagine, and it's hard to do a whiteboard here, and get it filmed. But if one of the models isn't fitting in such a way that the p-values are all skewed towards 1, and another model is not fitting in such a way that all the p-values are skewed towards 0, then when you combine them together, the ones that are close to 0 are inordinately influential on the combined inference, right? Because we're worried about stuff close to 0. And so if you combine stuff that's piled up near 0 with stuff piled up near 1, the zeros are going to win, unless you flatten their distributions. And so that's what the calibrators do. They're aware of the normal of the distribution skew, I suppose, coming out of the scorers, and they flatten them for one thing. But they do other things too, and Cole will talk about what else they do. And then it's a streaming setup, so when they see data, they score it, and then they update the model with the data. And so it's constantly trying to learn, and that's because network behavior changes a lot over time. And so these models have to be sort of streaming and lightweight and updating constantly. And then finally, what do we do with these things? So hunting. So we have a thing I've got to advertise, Microsoft Threat Experts. It's a managed hunting service that we provide to our enterprise customers. This is people looking through our alerts and telemetry to find attackers that we don't know about in our product. It's an admission that adversaries are agile and doing new stuff all the time, and we're not perfect in our detectors, and so we add a layer of humans on top. What those hunters like are prioritized lists. They don't want alerts. They want, that's the weirdest thing, and that's the second weirdest thing, and so forth. So that's what they get as output from these combiners, is a list of prioritized events that they can start with the idea that they're trying to find the unknown unknowns, the stuff that we don't know it's an attack or not, but it's really rare, and so you should probably look at it. That's been really successful. We are able to emerge or surface behaviors which we didn't know about, and just through the rarity in which the behavior is evident that we're able to surface these things. The other way is through our portal. So we threshold, and the thresholds can be dynamic, and I haven't really sketched them out here, but thresholding or quantiling on a set of scores is done, and then the ones that exceed a certain value get reported in a web portal to our security operations customers. So these are customers, security teams that are looking at a web portal all the time, and we're surfacing alerts, and they're responding to them, and that's where that goes. Questions about any of this? Yeah.
With the prioritized list that hunting teams use, you said you guys offer that as a service as a Microsoft. Can that be surfaced into customer portals and let the customer threat hunting teams work off that list instead of like the Microsoft guys?
Yeah. So that's a good question. So two ways we do that. So one is the threat hunters, our hunters, do surface those things they find through the same portal that our users have. So first, their results go to the same portal. That's sort of a trivia thing. But what you were really asking for is, do we enable our customers to do their own hunting? And the answer is yes. So in the portal, you have this thing called Advanced Hunting, which is a query language based on Custo, which is a Microsoft sort of SQL-like query system, where they can both dig into our alerts, but also the raw telemetry we're collecting about the enterprise. So yes, we enable them to do hunting as well. And in fact, I don't want to be I'm not a sales guy, but I'll tell you that our next offering that was announced at RSA is called Sentinel, Azure Sentinel, which is it's a SIEM. So it's a security event and incident management system in which not only can you hunt on the telemetry we're collecting, but you can put other log data in and do hunting in that way as well. Yeah. And in fact, one thing that's cool about it for the data scientists is it's got Jupyter Notebook support, so you can write Python, and I'm so glad that they did that. Other questions? Okay, let's keep going. Great questions. I think people are actually care, so that's nice. Modeling briefly, and I do have a list of sort of behaviors here. There's a few in there. We're statisticians on my team for the most part. We take sort of a distributional approach to the problem. We take a data generating approach to the problem. We're less interested in algorithmic solutions, black boxes. My team is less interested in deep learning than other teams at Microsoft, okay? And this is a choice on purpose for us so that we get explainability in our models carried all the way through to the detection. I am not saying that deep learning is a bad idea. I'm saying that for us in anomaly detection, we need to be able to explain every single decision we're making in order to surface that to the user. And in order to do that, we build models that based on the data generating process. It has periodicity in it. It has effects for time of day and day of week. Whatever the data is telling us, we want to model with parameters, and those parameters are useful when we report to customers. And so that's sort of a basic tenet for us. And it's pretty rare in the industry. I don't know of other teams that are doing this, honestly. Almost everybody else is using some kind of machine learning approach, an algorithmic approach, I would say, like deep learning or support vector machines, or pick your favorite black box. High resolution, I've sort of gone over these things before. I think this is sort of for the, for the perhaps not layman, but less sophisticated in the sort of statistical side of things. You know, what I'm trying to say here is that we model whatever the data generating process is. We're capable of modeling whatever you'd like. Because we borrow from a couple hundred years of statistics. In terms of the types of anomalies we pick up, there are categorical ones. For example, imagine you've got a web server. It's listening on port 80. It's listening on port 443, maybe some SMB management traffic. And then we see it listening on some other ports. Okay, so that's like a categorical anomaly. Okay, we see population anomalies. So I wish my team member had made the blue dots red and the red dots blue, because the blue dots are bad guys and the red dots are fine. But you can see that attackers stand out in the population from the rest of the population. Okay, they're far away in some idea. And typically, by far I mean with a distributional assumption under the hood. They're far in a probabilistic sense. And then time series. And so I'll talk about time series anomalies, and we happen to have a time series forecaster coming up next, so I won't beat you over the head with this, but it's just to try to sort of introduce you what we mean, what is a model here? And some of us know this, and it's sort of obvious, but for others, this here is an outbound number of connection attempts by a given server in one of our customer networks. The blue, that's the blue number of connection attempts. The orange is a model fit to the data. It's a hurdle model, negative binomial hurdle model with seasonality in it. And it's updating, so you can see that it's sort of adjusting to the data over time. It's learning about it. It's got some time of day, and I don't think this one has like weekly effects in it. So it's just learning. Yeah, it turns out that servers are more active in the middle of the day than they are at night, and that's important for the data. And that's part of why we build. This is the getting at the data generating process. The green is two standard deviations. Don't worry too much about that. Towards the end of that time period, you can see this enormous spike. It's super obvious to the human eye. It's a brute force attack by one of our customer compromised computers. It's not like they did it on purpose. They were compromised. They had a bot installed inside their enterprise, and it's attacking the internet. And our customers don't want to attack the internet. They really don't like that. And so this alert was indeed a giant spike in the outbound connection attempts that was part of a brute force attack. And you would think, okay, well, that doesn't seem very hard. It's actually not. If you build the right model, it's easy. But if you don't, this is actually quite hard to find. And part of it is just automating this, having per machine models that are aware of normal behavior. Because some servers will do this. They'll emit 4,000 outbound connections as part of their job, and it's fine. So just automating the awareness of what's happened in the past so that we can know that that's unusual for this machine, it's simple. It's not a very high-powered statistics, and it's very powerful at detecting attackers. OK, keeping on. Here's another one. Again, so this is inbound connection attempts. Not very many. We're not expecting very many. Just ones and twos, probably just ones over a long period of time. These are, the top is sorry, over here. I'm sort of ignoring you. I'll go over here. The top ones are failed connection attempts, and the bottom ones are successful ones. And this is a brute force, inbound brute force. They're trying to get into a computer by guessing passwords over and over. Is this your password? Is this your password? Turns out, yep, that was the password. They had a successful one, and this machine is now compromised. OK. Some more simple things. You're going to hear the complicated stuff from Cole. Simple things. We can extract. So this is a reconnaissance. Remember, I was talking about this port scanning. So this is a port scanning reconnaissance. They're inside the network. They're trying to find out what computer to connect to next, and they're emitting these sequence of are you listening on SQL? Are you listening on web? Are you available for RDP? These kind of trying different things, OK? Excuse me, I'm talking a lot. And so you can measure various things about the network and the operating system in order to quantify the rarity of stuff that's consistent with port scanning. So the distinct port count emitted by that machine, the distinct IP count. So you could, this is sort of the difference between vertical and horizontal port scanning, so it's a sort of a technical detail, but attackers will either try a lot of different services on a given machine, or they'll try a lot of different machines for the same service. And so if they try a lot on the same machine, that's called vertical, and if they try a lot of different machines, that's called horizontal. But this is doing both. By looking at the distinct port count and the distinct IP count, the connection count, the failures, the importance. We've got a weighted heuristic thing on the port importance. A couple other heuristics are Boolean values. And then we measure their frequency in the data. It's as simple as that. How often does this port count happen on the data? And divide by, statisticians, this is a secret about statisticians, is a lot of times we're just adding up the numbers and dividing by how many there are. And that's a case here where we're taking the mean. And then the same trick as before. There's a Fisher's p-value combination method to give us a distribution, to give us a score, which is compared against a chi-square distribution, and a threshold is applied. And anything weirder than that threshold gets alerted on, and this works like a champ. This is a simple, simple method that nails a bunch of attackers. And it's because of a distributional approach, as opposed to a heuristic or signature-based approach, or even a supervised approach, that just nails it. And I pity the attacker who does this kind of thing on our networks. We nail them, including some pretty bad, nasty behavior. You don't want Monero ransomware. You don't want it. It's not okay. It's a bad thing. OK. Yeah, we do lots of other stuff here. There's Markov transition probabilities between processes. So you can say, like, how often does this process call that process? And then how often does that process call a further process? And so you can sort of establish, models for process trees. We got these lol bins so living off the land binaries. So this is like things built into the system. On Windows, it's things like netstat. So if you run netstat, it'll tell you all the computers that your computer is connected to in the last X amount of time, right? And this is a way for attackers to discover where to go next, right? So they're called living off the land binaries. It's the attacker not importing any attack tools. They're just using system tools to move around the network and steal data. And so it's kind of hard to find attackers doing these things. We focus a lot on sort of lol bins behaviors. This is not a complete list. It's just to give you a feeling that, I don't know, we have many detectors deployed that are statistical at this point. Here's a few of them. And I think with that, thanks for listening, and I hope you have more questions. Thanks very much.
Any questions for Josh?
Thanks. You mentioned at the beginning of your talk about rarity and the times when that's just actually a normal factor of the system.
Yeah.
In your beautiful diagram with the feedback on the models, there wasn't a place where you kind of explained where the heuristics and the analysts were put in.
Yeah, and so you've found the bit that I hid from everybody, and the secret is that if I go back to the start of the talk, that's actually what the network looks like. And the graph I showed you, the pretty one which just had the attacker in it, is like this little tiny bit here, and there's all this other stuff. And what about the other stuff? Is that what you're asking, or? I'll go to the.
The next one, the system diagram, this one.
Okay.
So where do the heuristics come in? Are you putting it for the end user to apply themselves back in the corporate environment, or are you putting this into your data pipeline?
Sorry, you're asking about the non-attack behavior?
Sorry, separation between operational and statistical anomalies.
Ah, okay. Yeah, where do they go? Yeah, so that's a pretty big subject. We have about 700 detectors deployed. About 600 of them are heuristic in some way, and that they could be described by a decision tree with parameters. So if X is less than 56 and Y is greater than 137, set off an alarm. Those kind of things, right? They don't currently fit in here. These are purely anomaly based. They should though. And so we've done some thinking about score combination. And you can think of the heuristics as generating zeros and ones. They fired or they didn't. And Cole will have some things to say. Cole, are you going to have some things to say about this?
Yeah, I talk exactly about that. It will fit into here.
So let's defer that a bit. But the vision and the ambition is let's combine those things along with these more statistical things, along with supervised machine learning scores together. Yeah, good question. Yeah. It's a long way to walk, Mark.
Somewhat related. When you're going through this, it seems like you're only calculating one score for the system. Are you calculating scores for individual nodes, or are you calculating scores for individual bits of the system, or I mean, I guess what I'm asking is, at what scale are you calculating these scores?
Yeah. At the scale of every univariate behavior that we observe. So we keep most of our models univariate. I might be willing to consider bivariate, but for the most part, sort of each user logging, for a given user to log into a given computer from some other computer, that's a model that emits a score every time that happens.
But I guess, sorry.
And then what do we alert on?
Yes, I mean, I guess in this diagram here, you're taking k-scores, combining them in some way. Let's not worry about it. And then alerting or not. But are you Are those scores over the whole system?
Yeah.
Are they over an individual machine?
Right.
Sorry.
Yep, that's a good question. Yeah, no, that's a good question. So the answer is yes. That is, in this case, it is the number of inbound login requests that we alert on and report, and there is no combination. Okay. In the case of this one, there are several things that are combined together. In cases where the kill chain is expressed across multiple machines, we'll attempt through collaboration with our threat experts to combine the right things to cover the attack. So, if this full kill chain is expressed in the enterprise, we'd like to capture it in one single score.
Okay. But the combinatorics of doing that must be pretty hard, as
Yeah.
you've got millions of machines.
Yeah. So this is another talk, but I'll tease you on it, and there's some literature I can point you at to get at this. There is a graph subgraph identification problem. So you can imagine that you have scores covering the entire ecosystem, and now you're trying to find a subgraph of most anomalous scores. And that is another talk and another set of graph-based methods, but some things come to mind. Templates, so define, say, a path of length 3. And I think there's a few in here. You can see, A talks to B, talks to C, talks to D, talks to E. That's a path of length 5, where there are 4 edges, so length 4. Enumerate all paths of length 4 in the entire enterprise, calculate their combined score, and threshold those score distributions. That's one way to, and then you can also combine it with templates of stars. So these outbound, the set of outbound for a given node, that's another graph sub-template that you can enumerate everywhere, score all of those, combine those together, and you can actually find this. So that's one way, templates. Another way, greedy sort of enumeration, where you pick the weirdest alpha, start there, and try to grow out a subgraph of most anomalousness. But I guess you get the feeling that I'm separating the problem into two. One is establish a layer of scores, and second, find the most anomalous subgraph. And what I didn't say is sort of spectral graph methods. And the reason I'm not saying that is because we're doing active research and we don't want you to scoop us. I'm just kidding. You're happy to talk more about that if you'd like.
Okay.
Hi, one question. Okay, you mentioned just now early in the talk that you collect telemetry data on your customers' enterprise systems.
Yes.
So what kinds of data do you actually collect?
Those things. File hashes that are present on the network, on the data, on the enterprise, on the endpoint. Process trees, the full process tree. Network connection metadata, like connection level statistics. Registry changes, command lines, PowerShell usage, and 15 or 20 other things.
Right. So actually, do you collect things like syslogs, error logs, win logs,
Yes.
for example, resource usage as well, and stuff like that?
So we're at a lower level than that. So the things that go into those logs are driven by the event tracing for Windows, ETW, which is available for anybody. This isn't like special sauce. In fact, in the 90s, we got in a bit of trouble for not making this kind of stuff available to third parties. And so nowadays you can get the same kind of data that we get, but a lot of it is then compiled into Windows logs, security event logs, and so forth. So we're at a lower level, and the agent is in the kernel and has hooks into the drivers. But yeah, these things are what you get out of the event logs. We're sort of before that.
So when you're modeling the mality, is it always at the level of the enterprise that you're working with, or is there any kind of like hierarchical kind of, this is what goes on in a general enterprise?
Across enterprises. Yes.
Yeah, I mean, the reason I ask this is because it, like, I guess you're making the assumption that normal behavior is stationary. And I guess like for some enterprises, maybe that's not true. Maybe they move very quickly. Maybe they're just like a bit weird. And so, yeah, I wonder whether you use kind of like cross-enterprise information at some point.
Yes. So I showed you these. Where are they? These prevalence statistics, and you can think of like the prevalence of a file hash anywhere in our data is used to establish some of these scores. So that's sort of boring, but very effective. Other things are, though, that we can be sensitive to are sort of supply chain attacks. So I'll give you an example. There was a Target breach, the company Target, a few years ago, in which it was an HVAC vendor, a heating and air conditioning vendor, which had a credential that allowed them to log into Target's network, and the attacker phished the HVAC vendor's network, got a credential, got access, and then used that credential to log in a completely valid way into Target's network. That what we would call lateral between the HVAC vendor and Target's network. Yes, we can do those kind of things. It depends on whether that other customer is a customer of ours as well. But when we do, and so there's sort of active attack behavior that we can glue together. Then there's threat intel. And threat intel is a lot of things, but it's a feed of malware coming from everywhere. It's our extracted understanding of attack behavior that we can take from one thing that we saw somewhere and apply it to another. And some of these things feed into us by expertise teaching us about it. It's like they learn something and then they teach us about it. So I think there's, the answer is yes in lots of ways.
Okay, in the interests of time, I think we'll, and Josh's voice, we'll thank Josh again, if we may, please.